Welcome to another exercise in the workbook Statistics. This time with an exercise focusing on t-test for coefficients and the f-test. Let's have a look at the exercise. Here we have an airline asks you to study the relation between their fleet's age and yearly repair costs in 10,000 euros. To realize this endeavor, for a preliminary study you collect the data in the table below. So here we have more or less for 5 different planes, the age and the cost. And we can assume that the cost depends in one way or another on the age. So cost is the dependent and age is the independent variable. Well, with this cleared, our first task is use the method of ordinary least squares to estimate the regression line that describes the relation between the two variables. Second, calculate the respective coefficient of determination r squared and interpret it. Finally, third, use a suitable test to check whether the determined relation is significant for an error margin of 5%. Well, so let's start with the first part, with the regression line as such. Here, if we want to calculate the coefficient of a regression line, what we're going to do is first take the table and expand this for one additional column. And in this column, we're going to put the averages of the respective row. So here we're going to take the average for x, the average for y. Then we're going to add 3 more rows to the table. Or rather, in this case, only 2, but for later on we might need a third as well. So the first one would be by squaring all the x values. So here 1 squared, 6 squared, 11 squared, and so forth. And of this we're also taking the averages. Then we're going to calculate x times y. X times y, so 1 times 15, 6 times 50, 11 times 260, 9 times 150, and this one. Again, we're going to calculate the average. Later on, we're going to calculate as well the squared y values, but not at this point. Here, for the coefficients, we can start with the slope of the regression line. This formula for the slope is simply taking the average of x times y, so the 935, and subtracting from it, on the one hand, the average of x times the average of y. So those two multiplied. And all of this is then divided by, first off, the average of x squared, so 52.8, minus the average of x to the power of 2. So here it is 6.4 squared. That's this part here. If we calculate this, we get as a slope 24.375. This slope we can then use to calculate the intercept. The intercept we get by taking the average of y, so here the 101, and subtracting from it, first off, b, that's the 24.375 from before, times the average of x, that's the 6.4. So if we do this, we get as an intercept minus 54.808. That's everything there is to this regression line. So the regression, if written down, or the regression line, if written down, looks as follows, with this slope and this intercept. So once we have the regression line, we can then turn to the second part, to the calculation of the coefficient of determination, the r squared. To do this, I'm first going to copy the regression line, and then as well the table with the values we had before and with the additional column for the averages. Next, I'm going to add 1 row where I'm going to square all the y values and also taking the average thereof. And finally, the next line, that's actually something where we have to do quite a bit of work. We have to insert all the x values into the regression line and calculate an estimate for y. Those estimates for y, that's the y hat here. Those estimates for y, we're then going to square, giving us these values here. Of these values, we're also calculating the average. That's the value down here. That's actually now the chance where I can compare whether I did my calculations decently well. Because this value always has to be smaller than the value above it. So y squared is always larger than y hat squared. We're going to see in a moment why this is the case. Once we have this, we can just use the formula, the general formula for r squared, where we have the average of y hat squared, so the 17,200 something, minus the average of y squared, so the 101 squared. Below the fraction line, we have the average of y squared, so the 18,745, minus again the same y, or the average of y squared. So again, 101 squared, which we subtract from it. The result in this case would be 0.8279. So r squared of roughly 83%, meaning that we can explain with our model, or with the independent variable h, roughly 83% of the variance of our costs of y. Well, this r squared is defined as always being between 0 and 1. Can explain nothing, 0%, can explain everything, 100%. And that's the case why this value should be smaller than that one. Because if we look closely, we see if the average of y hat squared would be larger than the average of y squared, we would get a larger value above the fraction line, so the end result would be larger than 1, which, well, it cannot be. Well, with this cleared, we not only have a way to check whether we did our calculations correctly, but we also know how to interpret this. So while 83% looks quite large, we want to do an additional test to check whether this is actually large enough, whether this is actually a significant share of the total variance which we can explain. And that's what we're going to do with an f-test. So with the f-test, I'm going to use the information I have before, as in I'm taking the r squared, divide this by k, r squared, this is from the last slide, from part B. K is the number of independent variables. Well, we only have one x here, so we have one independent variable. Then we go with 1 minus r squared, so 1 minus this one gives me here. Then I have n minus k minus 1. N is the number of observations. K was 1. So 5 minus 1 gives me 3. If I calculate this double fraction, I will get 14.4317. That's our test statistic for the f-test. To really conduct a test, we still need a reference value. This reference value or reference statistic we get from the table. In the table we have to look up f, k, n minus k minus 1, 1 minus alpha. K was 1, n minus k minus 1 is 3. Then we have alpha. Alpha is the margin of error. The exercise text here said use a margin of error of 5%. So if we use 5% or 0.05, we get for the last value 0.95. So we look this value up in the table for the F distribution and find there a value of 10.128. That's our reference value. That's the value we're going to compare our test statistic to. That's what we do in a test decision. So here we see the test statistic is larger than the reference statistic. This means we can reject H0. H0 in the context of an f-test, context of regression, means that the model has no explanatory power. So if we can reject this, this means our model has significant explanatory power. Well, that's then everything there is to this exercise. I hope you enjoyed it. I say goodbye and see you next time.